Geologi merupakan fondasi utama dari disiplin ilmu kebumian yang mencangkup dan menjelaskan berbagai fenomena alam seperti lempeng tektonik, gunung api, dinamika permukaan bumi, hingga aspek kehidupan dalam perjalanan pembentukan bumi. Ilmu geologi hari ini telah berhasil menjawab berbagai pertanyaan dan tantangan serta kebutuhan dalam perkembangan dunia di berbagai lini, seperti eksplorasi dan eksploitasi sumber daya alam, pelestarian sumber daya alam yang berbasis kondisi natural dan keberlanjutan, penanganan dan mitigasi bencana alam, pembangunan infrastruktur berskala besar yang membutuhkan rekayasa kebumian, hingga perencanaan wilayah berbasis kondisi alam. Universitas Diponegoro berada di Kota Semarang, Provinsi Jawa Tengah. Universitas yang melestarikan semangat juang Pangeran Diponegoro ini mengusung visi besar sebagai universitas berbasis riset yang berskala internasional.
Departemen Teknik Geologi, Fakultas Teknik Universitas Diponegoro berdiri pada tanggal 4 Agustus 2004 atas surat keputusan dari Menteri Pendidikan Nasional. Hingga saat ini, Departemen Teknik Geologi telah menghasilkan lebih dari 700 lulusan dan telah tersebar di seluruh Indonesia dan juga di mancanegara. Departemen Teknik Geologi telah terakreditasi oleh BNPT dan juga tersertifikasi ISO 9001:2015. Visi Departemen Teknik Geologi adalah menjadi Departemen Teknik Geologi yang unggul di tingkat nasional dan juga internasional berbasis riset pada tahun 2024. Misi kami adalah melaksanakan pendidikan yang berkualitas dan profesional dengan meningkatkan iklim riset baik itu dosen maupun mahasiswa guna menyelesaikan permasalahan di masyarakat dalam bidang pengetahuan dan juga teknologi kebumian.
Melalui visi dan misinya, lulusan teknik geologi diharapkan dapat menjadi lulusan berkarakter komplit, communicator, professional, leader, entrepreneur, educator.
Kurikulum Departemen Teknik Geologi dirancang untuk menyelesaikan masa studi minimal 4 tahun. Kegiatan pembelajaran berupa pemberian materi di kelas, praktikum laboratorium, observasi langsung di lapangan, dan juga praktik magang di instansi maupun perusahaan.
Kegiatan pembelajaran di Departemen Teknik Geologi Universitas Diponegoro didukung oleh berbagai fasilitas fisik maupun non-fisik, mulai dari beberapa laboratorium dan perpustakaan khusus di departemen hingga laboratorium terpadu di universitas. Fasilitas pendukung lainnya seperti sarana olahraga, ibadah, kesehatan, akses informasi, dan wadah organisasi juga tersedia baik di lingkungan departemen maupun universitas. Berbagai macam prestasi telah berhasil diperoleh oleh mahasiswa Teknik Geologi Universitas Diponegoro, baik di tingkat nasional maupun internasional. Hal tersebut menjadi inspirasi bagi para mahasiswa dan tolak ukur dalam mendukung perkembangan serta kemajuan Departemen Teknik Geologi untuk menjadi institusi keilmuan yang terkemuka di bidang kebumian. Lulusan teknik geologi dapat bekerja di berbagai bidang seperti pertambangan, perminyakan, hidrogeologi, panas bumi, dan rekayasa geologi. Sebagai kontraktor, konsultan, akademisi, pegawai negeri sipil, hingga pengusaha. Di sepanjang perjalanannya, ratusan terbaik Departemen Teknik Geologi Universitas Diponegoro telah tersebar dan berpartisipasi serta berkontribusi di berbagai sektor. Kondisi tersebut tentunya tidak lepas dari peran besar Departemen Teknik Geologi Universitas Diponegoro yang telah membentuk lulusan-lulusan yang unggul dan dapat beradaptasi dengan perkembangan zaman.
Dari Ralanarko, saya alumni Teknik Geologi Undip angkatan 2006. Untuk karir secara profesional, saat ini saya bekerja di Pertamina Hulu Energy. Karir secara organisasi, saat ini saya diperkenalkan sebagai ahli
Tri Omega Pahlawan. Saya sedang bekerja di suatu perusahaan tambang mineral logam dan non-logam di daerah Kalimantan Tengah. Di situ saya menjabat sebagai exploration geologist.
Nama saya Widi, saya alumni Teknik Geologi Undip angkatan 2011. Saat ini saya merupakan peserta on-job training Pertamina Energi yang merupakan bagian dari program bimbingan profesi sarjana Pertamina Persero. Alhamdulillah, dengan Undip merupakan suatu tempat bagi saya untuk belajar lebih mengenai bagaimana caranya berpikir kritis dan juga mengasah bekerja sama dalam tim.
Karena teknik geologi Undip menawarkan atmosfer yang sangat positif dan kondusif bagi setiap mahasiswa untuk dapat mengembangkan diri dalam konteks technical skills maupun soft skills. Sehingga saya sangat merekomendasikan salah satu teknik geologi terbaik di Indonesia saat ini adalah teknik geologi Universitas Diponegoro.
Dosen-dosennya itu sangat mensupport kita untuk bisa lebih baik, untuk bisa survive nantinya setelah lulus.
Terima kasih banyak Teknik Geologi Undip.
Bravo, Geologi.
Menjadi instansi pendidikan yang terkemuka dan dapat memberikan kontribusi terbaik untuk negeri bukanlah hal yang mudah. Berbagai perjuangan dan pembuktian akan terus hadir di sepanjang perjalanannya. Ini adalah kesempatan Anda untuk bergabung, belajar, dan bersama-sama menjadi insan terdidik, terkemuka, dan berkarakter komplit. Communicator, profesional, leader, entrepreneur, educator. Dalam rangka berkontribusi untuk kemajuan bangsa dan dunia keilmuan. Geologi merupakan fondasi utama dari disiplin ilmu kebumian yang mencangkup dan menjelaskan berbagai fenomena alam seperti lempeng tektonik, gunung api, dinamika permukaan bumi, hingga aspek kehidupan dalam perjalanan pembentukan bumi. Ilmu geologi hari ini telah berhasil menjawab berbagai pertanyaan dan tantangan serta kebutuhan dalam perkembangan dunia di berbagai lini, seperti eksplorasi dan eksploitasi sumber daya alam, pelestarian sumber daya alam yang berbasis kondisi natural dan keberlanjutan, penanganan dan mitigasi bencana alam, pembangunan infrastruktur berskala besar yang membutuhkan rekayasa kebumian, hingga perencanaan wilayah berbasis kondisi alam. Universitas Diponegoro berada di Kota Semarang, Provinsi Jawa Tengah. Universitas yang melestarikan semangat juang Pangeran Diponegoro ini mengusung visi besar sebagai universitas berbasis riset yang berskala internasional.
Departemen Teknik Geologi, Fakultas Teknik Universitas Diponegoro berdiri pada tanggal 4 Agustus 2004 atas surat keputusan dari Menteri Pendidikan Nasional. Hingga saat ini, Departemen Teknik Geologi telah menghasilkan lebih dari 700 lulusan dan telah tersebar di seluruh Indonesia dan juga di mancanegara. Departemen Teknik Geologi telah terakreditasi oleh BNPT dan juga tersertifikasi ISO 9001-2015. Visi Departemen Teknik Geologi adalah menjadi Departemen Teknik Geologi yang unggul di tingkat nasional dan juga internasional berbasis riset pada tahun 2024. Misi kami adalah melaksanakan pendidikan yang berkualitas dan profesional dengan meningkatkan iklim riset baik itu dosen maupun mahasiswa guna menyelesaikan permasalahan di masyarakat dalam bidang pengetahuan dan juga teknologi kebumian.
Melalui visi dan misinya, lulusan teknik geologi diharapkan dapat menjadi lulusan berkarakter komplit, communicator, professional, leader, entrepreneur, educator.
Kurikulum Departemen Teknik Geologi dirancang untuk menyelesaikan masa studi minimal 4 tahun. Kegiatan pembelajaran berupa pemberian materi di kelas, praktikum laboratorium, observasi langsung di lapangan, dan juga praktik magang di instansi maupun perusahaan.
Kegiatan pembelajaran di Departemen Teknik Geologi Universitas Diponegoro didukung oleh berbagai fasilitas fisik maupun non-fisik, mulai dari beberapa laboratorium dan perpustakaan khusus di departemen hingga laboratorium terpadu di universitas. Fasilitas pendukung lainnya seperti sarana olahraga, ibadah, kesehatan, akses informasi, dan wadah organisasi juga tersedia baik di lingkungan departemen maupun universitas. Berbagai macam prestasi telah berhasil diperoleh oleh mahasiswa Teknik Geologi Universitas Diponegoro, baik di tingkat nasional maupun internasional. Hal tersebut menjadi inspirasi bagi para mahasiswa dan tolak ukur dalam mendukung perkembangan serta kemajuan Departemen Teknik Geologi untuk menjadi institusi keilmuan yang terkemuka di bidang kebumian. Lulusan teknik geologi dapat bekerja di berbagai bidang seperti pertambangan, perminyakan, hidrogeologi, panas bumi, dan rekayasa geologi. Sebagai kontraktor, konsultan, akademisi, pegawai negeri sipil, hingga pengusaha. Di sepanjang perjalanannya, ratusan lulusan terbaik Departemen Teknik Geologi Universitas Diponegoro telah tersebar dan berpartisipasi serta
Oke, baik, selamat malam. Sebelumnya saya ingin mengetes dulu ya, apakah suara saya bisa terdengar dengan jelas. Mas Redi, suara saya kedengaran nggak?
Sudah Pak, sudah. Mantap.
Udah dengar, oke. Ya, baik. Assalamualaikum warahmatullahi wabarakatuh. Selamat malam dan salam sejahtera untuk kita semua. Saya ucapkan selamat datang di acara webinar series ya yang diselenggarakan oleh Teknik Geologi Universitas Diponegoro. Selamat malam kepada Bapak dan Ibu dosen dari program studi Teknik Geologi Universitas Diponegoro. Selamat malam juga kepada seluruh peserta ya, mungkin dari luar instansi, dari berbagai macam instansi yang hadir pada kesempatan malam hari ini, dan selamat malam juga kepada seluruh mahasiswa ya yang mengikuti acara webinar ini. Jadi webinar ini merupakan salah satu rangkaian dari acara visiting profesor yang diselenggarakan oleh Teknik Geologi dengan mengundang pembicara dari universitas-universitas terkemuka di dunia. Baik, untuk sebelum dimulainya acara webinar ini ya, sambil menunggu pembicara, pada kesempatan malam hari ini webinar akan diisi oleh Profesor Magaly Koch dari Boston University yang akan menyampaikan materi tentang Geological Remote Sensing Application in Aeolian and Fluvial landscapes. Bagi teman-teman yang mungkin baru pertama kali mengikuti webinar yang disampaikan oleh Profesor Magaly, saya informasikan bahwa Profesor Magaly sudah beberapa kali menjadi narasumber dalam acara webinar ini dan telah menyampaikan materi-materi tentang remote sensing, yaitu basic-basic tentang geological remote sensing, itu mungkin dilaksanakan 3 minggu yang lalu, dan juga tentang aplikasi geological remote sensing di bentang alam tektonik dan vulkanik yang disampaikan 2 minggu yang lalu. Ya, jika teman-teman semua tidak mengikuti acara tersebut, atau mungkin ingin ingin mengakses rekaman dari acara webinar tersebut, dapat mengunjungi kanal YouTube kami, yaitu di Geologi Undip, seperti itu. Dan juga sekalian juga saya sampaikan di sini nanti bahwa acara webinar ini akan dibagi menjadi 2 sesi seperti biasanya, yaitu presentasi dari pemateri, yaitu Profesor Magaly, dan nanti akan dilanjutkan dengan diskusi dan tanya jawab bagi teman-teman dan audiens yang terhormat. Jika ingin memberikan pertanyaan nanti bisa menulis pertanyaan di kolom chat ya, dengan ketentuan atau format yang nanti akan disampaikan oleh panitia. Atau juga bisa dengan cara raise your hand, nanti akan kami berikan kesempatan untuk memberikan pertanyaan seperti itu. Dan untuk materi presentasi dari Profesor Magaly nanti akan di-share menjelang acara ini berakhir ya. Juga daftar hadir nanti juga akan di-share menjelang akhir-akhir sesi dari webinar ini. Jadi dimohon untuk tetap menunggu acara ini sampai selesai, begitu ya. Dan nanti kami mohon juga untuk kesediaannya untuk mengisi daftar hadir, begitu ya. Baik, sambil kita menunggu Profesor Magaly hadir bersama kita, mungkin Mas Redi bisa kembali memutar video tentang teknik geologi tadi atau bagaimana? Monggo.
Oh, nggak bahasa Inggris tadi. Iya, iya. Boston. Oh iya, iya. Kok
Oh ya, nanti kepada seluruh partisipan dimohon untuk tidak atau untuk memute-kan mikrofonnya ya, dan mematikan videonya ya. Mohon sekali dengan hormat untuk mematikan mikrofon dan mematikan video untuk menghindari mungkin sekedar gangguan-gangguan ketika berjalannya webinar. Terima kasih.
Hello, can you hear me?
Hello, Professor Magaly.
Yes, let me share my video with you so we make sure you
Okay,
can
thank
see
you.
me.
Yeah.
All right. Okay.
Okay, I see you.
Okay, good.
Yep.
Excellent.
Okay. Good morning, Professor Magaly. How are
Good
you?
morning. Very good. How are you?
I'm fine, thank you. Okay, welcome to our webinar series again. Thank you for your willingness to be our special guest. It's an honor to have you to be our speaker again and again today.
All right.
I'm sorry, can you hear me clearly? Because it's raining hard here.
Oh, no, I can hear you very clearly. Yes, I can hear
Okay.
also some background noise.
Okay,
Is that
thank you.
rain?
Yes. Thank you very much. Okay. Allow me to introduce myself. I am Winarno, and you can call me Tri. I
Three.
am from, yes, Tri. Tri. I'm from,
Yes,
yeah.
that's easy for me to remember. Very short. Usually
Okay.
Indonesian names are very long.
Oh, yeah. It's so simple. Okay, I'm from Department of Geological Engineering, Universitas Diponegoro, and I will be your moderator for today's webinar. Okay?
Okay.
Yep. Now, allow me to open this webinar. Good morning, Professor Magaly Koch, and good evening to all the participants of today's webinar. This webinar is the main series of visiting professor program conducted by Department of Geological Engineering, Universitas Diponegoro. And the speaker for today's webinar is Professor Magaly Koch from Center for Remote Sensing, Boston University, USA. And this is the last session maybe for Professor Magaly to give us knowledge about remote sensing. And for your information, and in the previous series of this webinar, Professor Magaly has given us a lot of knowledge about remote sensing, such as 3 weeks ago, Professor Magaly has given us knowledge about the basic of geological remote sensing. And 2 weeks ago, Professor Magaly has given us about the application of geological remote sensing in tectonic and volcanic landscape. In case all those participants miss all of those material, you can visit our YouTube channel at Geologi Undip. And today, Professor Magaly will give us a very, very interesting topic about the application of geological remote sensing in the Aeolian and Fluvial landscapes. And before we start this webinar, I will give you some information about Professor Magaly. Maybe this is the first time for most of participants to join this webinar with Professor Magaly. I will give you some information about Professor Magaly, just a little bit, yeah. Professor Magaly is from Center for Remote Sensing of Boston University, USA, and her academic training are Master Science in Geology from University of Cologne, Germany in 1986, and then a diploma in groundwater hydrology from Polytechnic University of Catalonia, Barcelona, Spain in 1987. Then she got the PhD degree in geology from Boston University in 1993. And her teaching experiences are, she is the lecturer in Boston University, of course, and Tufts University also, Harvard Extension School, and so many guest lecture and training course in a lot of university. And she has conducted a lot of researches in remote sensing, and she wrote a lot of paper about remote sensing also. Okay, and to all the participants, before we start the webinar, I will give you some rules in this webinar. First, all the participants must mute the microphone and turn off the video to avoid the inconvenience during the webinar. Then the question and answer will be held after the presentation. You can ask your question by write your question in the chat box, or you can raise your hand and we will give you chance or time to ask your question. And then we will share the material or the file presentation of Professor Magaly near or before the end of the presentation. And also the attendance form, we will share the attendance forms before the webinar is ended. So please stay with us until the end and don't forget to fill the attendance form. Okay, without wasting longer time, it will be better if we start this webinar soon. Professor Magaly, the time now is yours.
Thank you very much for this nice introduction. And it's always a pleasure to be invited to give a lecture, or, you know, unfortunately, I'm not able to visit your country right now. As you know, travel restrictions exist worldwide, but hopefully next year. I'm gotten used to travel to Indonesia every year, so it feels very strange for me not having the opportunity to do it this year. But these Zoom, lectures or meetings are actually also a nice way to keep in touch, with my UNDIP colleagues, but also students, and basically to contribute to improve the educational content of your department, and also to serve to sort of share the type of research we do here in our center and so on. So I see these guest lectures not only a way of contributing to the educational component of your program, your degree program, but also a way to share our projects here in Boston University, and specifically in the Center for Remote Sensing. I have been associated to the center for decades now.
Yeah.
So, okay, so that was my introduction. So let me share my screen if I can.
Okay.
And I think you should see my screen right now, and my presentation in a minute. Okay, and let me get the first slide and put it on presenter mode. Okay, can you see my slides clearly?
Yeah, yes.
Okay.
Okay. Clearly.
Okay, good, excellent. All right, so yes, I have been giving some lectures about the fundamental aspects of geological remote sensing and the techniques. I talked a bit about the image processing techniques we use to highlight the geological features on images and so on. And today I would like to give you an example of research activities we have carried out in arid environments. And it may sound a little bit strange to talk about fluvial features in the desert, right? Because as you know, deserts usually don't necessarily show surface water. But we all know that, for example, in Egypt, it's not the only country, but it's one of the countries that heavily depends on a river, the Nile River, right? And so that's the current river that exists in Egypt. But in ancient times, in geological times, there were many other river systems that contributed to recharging the groundwater in Egypt. And so this talk is about a couple of, not just one project, actually a series of projects I have conducted in Egypt for the last 25 years, something like that. No? So I hope that with these examples, I will show the advantage of using remote sensing together with field survey. I think in my previous lectures, I emphasized that remote sensing is possible to use as a tool without going to the field, but you only get so much information out of an image. If you have never been to the site, it's kind of hard really to interpret images fully. No? So the surveys, the field surveys are really incredibly important for us to do a better job in interpreting images. Okay, so this talk is about mapping and understanding the hydrological history, if you want, of a desert area. And we're after fluvial features that are currently not necessarily visible because they're covered by Aeolian features, meaning sand sheets and sand dunes. No? And the purpose of this study is to understand the groundwater potential in Egypt. So just as sort of a reminder, I will quickly go over the remote sensing basics just to refresh your memory a little bit. No, so this is summarizing what we already discussed in my previous guest lectures, but I will focus on water resources, and I will introduce this by talking a little bit about the global water or food crisis. Water and food, they go together. They're critical, especially in areas, in regions where there is not enough water. In order to grow food, in order to carry out agricultural activities, you need water. So irrigation water, basically. And then I will show you slides about my studies in Egypt, in the Western Desert of Egypt. So just a slide here to refresh what I've been talking about in the last couple of meetings we had. Remote sensing is a technology, right? It's not necessarily a discipline, right? There are many researchers from many different disciplines that use remote sensing. Geologists are just one of them, one of the disciplines. But if you look at this slide, you can see how remote sensing data is being used in, for example, to monitor and assess air quality, right? And that can then be an important source of information for those who are studying public health issues, right? So a discipline completely removed from geology, right? They're looking into assessing the changes or the characteristics of the atmosphere, of the air, basically, right? But there's always a relationship to geology, even if you look at the air quality. Why? Because, for example, if you have a volcanic eruption, right? Well, all the what's coming out from from the volcano, ashes and so on, will obviously contaminate the atmosphere and eventually may have an impact on people's health, right? So even if you're looking at these different aspects that where remote sensing data can contribute information, somehow they're related. So it's never, when you look at the individual disciplines and you think, oh, I have nothing really to contribute to, let's say, biology, or I don't know, epidemiology, or whatever discipline. Well, you know, chances are that that's at some level there is some aspects where both disciplines may have something in common, right? And I just gave one example with respect to air quality and how that can be linked to some geological phenomenon, right? And then, of course, water resources, that's my area of expertise, especially in arid environments, although now I'm working more in tropical environments like Indonesia, right? And I'm looking into floods and flooding problems, coastal flooding and land subsidence. But during my professional life, I have actually dedicated a large portion of my time to investigate and you know, groundwater resources in arid environments. You know? And then, of course, land use and land change and ecology, land cover change. In this case, my interest is agriculture, especially irrigated agriculture, because that's what you see on the surface, on the land surface, whereas groundwater is hidden from the, you know, from the land surface. I mean, it's hard to have a device, or it's more difficult to detect what's under the land surface than what's on the land surface. And agriculture is easily detected with these images, with these remote sensing sensors, and they can tell us something about the water resources they tap. They, you know, the plants need, the crops, they need water to grow. And where does this water come, right? So that's something I'm interested in. So I mentioned that remote sensing is technology. It allows us to collect data. And the data is first not necessarily immediately in a way that we can interpret it, right? So think of satellite measurements as the technology that collects information. It actually collects data, and it does that in a continuous way, right? So it's all these satellite systems that are, you know, constantly orbiting the Earth and collecting data. And so you can imagine the enormous, I mean, incredible amount of data that is being collected. And that imposes a problem, because we got to somehow analyze the data, right? And that's where big data analytics and tools and algorithms that can actually make sense of these big data are so important, no? And we now live in an era where we have artificial intelligence, we have machine learning techniques, you know, that help us to sort of make sense out of huge volumes of data, right? And when I say make sense, it means we want to extract information from the data that we can use in applications. And as you can see here, you see the processing workflow, right? From collecting data and then converting this data into what we call satellite products or image products. And products, the word product means that somehow some processing was done to convert the measurements that was carried out at the satellite. And what type of measurement is it? It's basically the sensors are collecting or are measuring energy, right? It's basically electromagnetic radiation that they are measuring as they fly over the Earth's surface. And that measurement, that energy measurement needs to be converted into an image, right? And the image needs to be converted into a map. And that map, for example, here we have a map that was created that specifies which areas are, prone to flash flood if heavy rainfall happens, right? And there are many, many steps, right? And that is critical. This map is critical for, local governments or decision makers and so on to issue a flash flood warning, right? And to prepare the population for potential, hazards. All right. And I think, and I also showed this series of Landsat scenes over an area in Saudi Arabia. So this is my introduction to the arid environment here. And you can see a nice colored image, a time series. I will show you in a minute how this region is changing. And just let me remind you that what you see here is a false color composite Landsat image. So the colors, they look very, very, very different from what we would see if we would fly over this area, right? We would see a less colorful desert area, right? And the way and the reason this is so colorful is because the sensor that captured this image uses some wavelengths or uses some spectral regions that are that are not visible to our naked eye. Okay, and in those regions, non-visible regions of the spectrum of the solar spectrum, these landscape features, they look very colorful. We humans cannot see it this way because we are limited to the visible light portion of the spectrum, right? But we can build sensors that can detect light in beyond the visible portion of the spectrum, the solar spectrum. And that reveals many landscape elements. So here, for example, in the northern part, let me change my pointer to make it a bit thicker. Here we see a depressed area, the terrain is lower, and so there is a lake, a saline lake or semi-saline lake that fills up with water, as you see here in the dark area. As soon as the water table, intersects the terrain, no? And where's this water coming from? Well, this is water being supplied by the groundwater, and it's coming from the surrounding highlands. So the surrounding highlands are here. This is higher, much higher, and they contribute water whenever it may rain in the mountains. It may not rain here because it's too low, but further to the left, there's a mountain range, and the peaks of the mountains do get occasionally some rainwater, and that rainwater will then either infiltrate the ground and then sort of recharge the groundwater, the aquifer, and then basically discharged here in the lowlands where you have these saline lakes. Or if there's a very intensive rainfall, it may run off along these drainage systems. No? And what's happening here is that this area has been used actually since ancient times for agriculture activities. And you can see that here with these green patches. So those are agriculture fields, and the farmers learned how to make use of the near surface groundwater, no? And they found that along these drainage lines here, which are dry, they don't carry surface water, but very close to these drainage lines, not too far from the ground, there is some groundwater. So they dig some shallow wells and they use that for irrigation. They learned how to use that water for irrigation. So this image is from 1984 or something like that. And then I show you the sequence and how the agriculture activity changed here. And so you can see that the traditional way of farming shows crop fields with very different shapes and patterns than those that are occurring further away, more towards the desert plain area. And the round circles indicates that these fields are being irrigated using a sophisticated irrigation system, right? So they get their water, the irrigation system gets their water from very deep wells that pump the water out, and then they use it for irrigation. And that has a consequence. This highly mechanized agriculture activity has a consequence on the hydrology of the region. So this is the traditional non-mechanized or not highly mechanized agriculture activity, and this is highly and sophisticatedly mechanized agriculture activity, and has an impact on the water in the lakes. And you can see how the lake is drying as we look at more recent images. And this is one from, I think, maybe 8 years ago. No? And you can see that even here now, the traditional agriculture activity has changed. It's no longer the way farmers used to do it hundreds of years, because there's no near surface water available. All the water, was basically used for irrigation. And so that had as a consequence, the water table dropped. And now the only way to irrigate the fields is no longer by tapping these, wadi, near surface water flow along the wadis. These are called wadis in the Arab world. So they have to drill deeper and exploit water from deeper aquifer levels. And that has the negative consequence on the natural lake system here. So it's no longer being recharged. And you see here also a city developing, right? Okay, so this was an example from an arid environment and how they are using water, groundwater specifically, for irrigation. Now, I want to talk a little bit about the global water crisis, right? It's something we have been seeing in the news and so on. And what does it mean, global water crisis? So let's look at our planet from space. And you can see that it looks very blue, right? Blue and white. And this view is actually not showing a satellite, one single satellite image. It's actually a collection of satellite images that were stitched together, mosaiced together to give us this very nice view from space. And it's focusing on, not on land, it's focusing on the Pacific Ocean. And so this is to show you that our planet is actually full of water. It's actually called the water planet, because we have so much water, on our planet in different forms, in liquid form, in frozen form, and also as a vapor. And you can see the cloud formation. So the clouds are full of water. You see the oceans, right? And then you see the caps here, the polar caps, frozen water, right? So how come that we talk about a water crisis if we have so much water on our planet, right? And if you have been, following the news and so on, and also discussions that often at between governments, right? Negotiating water rights. I will talk about that in a minute. What that means, water rights, when governments have their negotiations of how much water from a river system each country can tap, right? That's very important in North East Africa. But before we go into that, let me just give you some statistics here. And the UN, this is mostly based on UN United Nations report. They say that basically 1 billion people around the world don't have access to safe drinking water, right? And many more have access only through communal water supply systems. So if I take Africa as an example, if you go to the countryside, you see that towns and villages, they don't have running water at home, right? They need to go to the town or village, well, central well or water supply system to collect water. But another problem is not so much having access to water or running water, it's also the quality of water. And I believe that in tropical countries, they're also facing, especially along coastal regions, facing this issue. And that has to do with the fact that the water gets contaminated. If you live along the coast and the population is exposed, for example, to sea level rise, right, or to tidal flooding, as the case in northern Java, what happens is that the seawater intrudes, and contaminates the fresh groundwater. And that's a problem for the population. They don't have access to good quality water, right? Another problem with the flooding is, of course, if you have highly urbanized coastal areas, that with the tidal flood, the canal system, the sewage canal system, and so on, that usually discharges into the sea, right? All of a sudden gets flooded and is no longer discharging where it should discharge, but it discharges where it shouldn't be discharging, which is in the city, right? So there you have contamination between, storm drainage systems with sewage systems, and it's a whole mess. So even if you live in a region where it rains a lot, it doesn't mean that the population has access to, high quality drinking water or safe drinking water. So over 2 billion people are living in water-stressed countries, right? Don't have access to appropriate sanitation. Big problem. And this problem will increase in the future. And it will increase not only because the population is increasing, of course, more people, bigger cities, more problems, but also because we're facing, climate change. And the changing climate may no longer recharge our aquifers the way it did, a few decades ago. And then closely linked with water is food production. Food and water, they go hand in hand. So the global water crisis may also cause a global food crisis, because if you don't have enough water to irrigate your fields and so on, or especially in semi-arid environments, then you cannot feed the growing population. So water is a necessity, and it cannot be substituted. It cannot be substituted by something else. It's not like, for example, oil. We have, or at least older generations have lived through some, oil crisis in the past. But we learned to actually search for some solutions, and now we're trying, or now I mean the governments are trying to develop some alternative resources to oil. But the problem with water is we cannot substitute it. We cannot just create something similar to water. And it's going to affect arid and semi-arid areas, more than tropical environments, because arid, semi-arid areas, they suffer disproportionately more from climate change than tropical environments. Or tropical environments also, but desert areas, they're very sensitive to climate change, much more sensitive. And the UN, the United Nations, they came out with some criteria how to measure water-stressed countries. They say they established sort of a water poverty line. They say, after studying, the issue, that one person needs at least 1,000 cubic meter of water per year, no? And that's what's shown here in the legend, no? So they say that the poverty line is somewhere between these two colors here. And then they looked at the different countries and how much water people, inhabitants, have per year. And you can see the lighter colors are obviously where you have the big deserts, the Saharan desert and so on, right? But also there might be some other regions, for example, here in Mexico, they're not right now under the water poverty line, but very close. So, and so of the 15 most water poor countries, 10 of them are in the Middle East, right here. And my research area has been in the last 25 years, Egypt. And if you compare that water poverty line map with the water use for irrigated agriculture, you will see some correlation. So this map here shows you with these pies, they're actually colored, regions in the world where they're using water to irrigate the fields. So not only rainwater. Rainwater would be shown in green. This is green means that percentage of the pie uses basically in situ water, rainwater for irrigation. Blue means that they're using river water to irrigate the fields, and then dark blue means they're using groundwater for irrigation. And groundwater is the only one from all three colors that is non-renewable in those arid environments, right? And the size of the pie indicates how much crop water use is necessary. So how much irrigation needs to be, carried out to grow, food. And here in the Saharan and Middle East area, you see that the very dark blue, and also here in this area, I think it's Iraq, India, Pakistan, and Kazakhstan. You see that the dark blue is quite high, the percentage of groundwater, and especially here in the Arabian Peninsula, and then here, not so much in Egypt, as you can see, because Egypt has the huge advantage of having the Nile, the River Nile. The River Nile is a life-supporting natural system. Without the River Nile, Egyptians couldn't survive. And let's take a look at the Nile Basin. The Nile Basin is a huge basin, huge. And there are like 11 countries that share the Nile basin. 11 countries depend on the Nile, right? So a lot of, you can imagine, a lot of negotiation is carried out between these countries in terms of how much water they can extract, they can basically use from the Nile without affecting the neighboring country, right? And this map also shows you the location of very important dam systems. So the Egyptians learned, a lot about irrigation in ancient times already. 2,000 years ago, 3,000, or even more. They learned how to use the Nile for irrigation, right? So they have a really an ancient history of managing water, right? But also other countries, Sudan and so on, they rely on the Nile, and they learned that the Nile river, the water level in the Nile river changes within a year. There are some seasons when the water level rises, and then there are some seasons when the water level drops, and also some seasons when there's flooding. And the flooding is actually good because it brings all the nutrients to the soil. It basically floods a huge plain area, the floodplain basically of the Nile, and then deposits these silts, and that's important for agriculture, right? Because the soil also needs to be renewed once in a while so that you can grow your crops. The problem here is that you got now about 400 million people living in these in this Nile basin area, right? And there's a projection that says that by the year 2050, there will be twice as much, so 1 billion people that will depend on the Nile, right? And that puts a lot of stress on the available water resources, because some of the Nile water is being diverted into the agricultural fields, and that may have an impact on the water level, the Nile water level, right? So if and in addition to that, some of these dams are built for not only for agriculture purposes, they're built for generating electricity. And that's the case in Ethiopia, where they have built many, as you can see, many dams, right? And especially in here, in this area, the upper Blue Nile area, which is a critical area. This small sub-basin contributes more than 50% of the water that eventually flows into the Mediterranean Sea. So this is the recharge, a high recharge area, right? More than any other region. So they built these dams to produce electricity and sell it to neighboring countries, which is a good income for in this case for Ethiopia. But the problem is, what effect do these dams have on agriculture activities in the lowlands, right? So, and then in addition to that, not only to human intervention with the waterways, this is one thing you have to keep in mind. The other thing is also, climate change. And climate change means less rainfall. And if there's less rainfall here in the highlands of Ethiopia, there's less surface water. Okay. Any questions so far? Because I'm going to show now some slides of about Egypt.
Egypt, Aswan.
Yes.
No.
Okay. All right. So the projects I have been involved where to evaluate basically the groundwater potential of desert areas, but the desert areas that are not too far away from the Nile. And this is because, first of all, the only fertile land in Egypt is basically where you have the Nile Valley, right, and the Delta. So those are, you know, the green areas here and also along the coast indicate where you have fertile land. And of course, most of the people live close to fertile land. So most cities are located along the Nile, right? But the government, the Egyptian government, faces a big problem because this is fertile land and it's needed to grow food, right? But if you have, you know, an increasing population occupying fertile land, then you don't have enough space to for agriculture. So there's a conflict between growing population and cities expanding, and basically by expanding these you know, urban areas, you're removing fertile land, right? You're basically paving over it, right? And it cannot be used for agriculture. So the government is trying to find an incentive for people to move away from the Nile Valley, no, and keep it for agriculture activities, and move the cities slightly away, right, and use the desert area to build their cities, right? But in order to do that, people need access to water, right? And you cannot divert river water very far away from the river, because the terrain is not flat, and you know, it's very expensive to pump up the water, right? So they're looking for groundwater, and that would be fossil groundwater, because you know, right now there's no recharge occurring. But in previous geological time, the climate was different. This desert area was actually not a desert. You know, 10, 20 million years ago. It was more a savanna type of environment. So this is here, these pictures are here showing some activities that the Egyptian government is sort of implementing. And you see that along the Nile on the western side, this sort of whitish area indicates where you have flat, you know, plains with soil, you know, that can be used for agriculture. You know? So the geologists, they have mapped this area, and they found that along these narrow, sometimes wider, whitish areas, there is good quality soil for agriculture. The problem is that there is not enough water. And so the government has been drilling for water, and you can see here the agriculture fields, you know, pictures from Google, highlighting where they are converting the desert into agriculture. Here you see an early stage of development. First, they have to build the infrastructure, not only roads, but also canal systems. They have to drill for water, and then and sometimes if it's close to the Nile, they don't need to drill for water. They actually divert some of the Nile water into these fields if the topography allows for natural flow without pumping. There's a law in Egypt that you cannot pump water up more than 80 meters above the Nile River, right? It's not allowed. So our study focused on Aswan, which is right here. So this is this here, and here you have Lake Nasser. And just to give you an idea of how the water in Lake Nasser is being used. So this is based also on agreements with neighboring countries. So Egypt has a secured allocation of Nile water in the range of 54 billion cubic meters, I think, per year, I think. So neighboring countries, they need to make sure that the Lake Nasser, you know, has a volume of 54 billion cubic meters, right? And this water is then used for ensuring navigation in the Nile. So the Nile water level needs to, you know, always have you know, a certain level that allows ships to navigate. So it cannot drop too much, because then ships can no longer navigate. So you need to make sure that a portion of this water ensures enough flow, right? And of course, a large portion of the Nile water flows into the sea, as you can see here. But that's important, because if you don't have enough Nile water flowing into the Mediterranean Sea, then you have seawater intrusion, right? So you've got to have something pushing back the seawater, you know? And why is this important? To, you know, keep the seawater intrusion basically controlled. If you look at the Nile Delta, this is basically the main source of food production, right? Egypt couldn't be surviving if it wouldn't have this Nile Delta and use it for agriculture. So if you have seawater intrusion here, you run into a big problem. So you need to have enough water flowing into the sea. And then, of course, a lot of water is being used for agriculture, right? Actually, in Egypt, 95% of the Nile water is used for agriculture. It's basically all the water they can divert from the Nile River is being used for agriculture. And only a small percentage is used for, is coming from groundwater. And this groundwater is used to convert desert areas into agriculture, but it's still a small portion. And then some of the water, of course, is used for municipalities and industrial uses and so on. And quite a high number is evaporates. This is a big problem in desert areas. When you have an open water surface, immediately the water evaporates due to the sun radiation. And here a few pictures of the dam in Lake Nasser. And here the team, this picture is already some years old. Here on the left is actually a hydrology professor from Suez Canal University. And here on the right is actually a former PhD student of mine, but he is now an associate professor in the geology department in Port Said University. And I'm here in the middle. And so the one of the tasks we were asked to do for this project was to analyze the desert plain area near Aswan. Aswan is here. This is the Nile, right? And there's a huge plain area that is higher up, at least 100 meters above. This plain is 100 meters above the Nile, right? So no canals can be built to basically contribute Nile water to this plain and convert this into agriculture because it's too high up, right? And I mentioned this law in Egypt that prevents that from happening. And you can see that they have expanded a little bit the agriculture into the Western desert, but these are lower terrains. No, they're not so high up as here. And if you look at the geology of this area, you see that it only shows basically the three different surface sediment classes. It shows you the sand sheets, medium to coarse sand here in green. And then it shows you sediments with gravel. Gravel is always an indication that at some point there was some water, surface water flowing. You know? Gravels are deposited by either by rivers or delta systems, right? So they're always an indication of fluvial activity. So you find here sediments with a lot of gravel, and then here a few patches with a mixture of gravel and sand. No? So this is the official geological map, and it doesn't really classify this area in detail, right? And on this picture, you see also that the plain is surrounded on the right by the river Nile. On the left, it is bounded by an escarpment. You know, this is actually another plateau. It's a limestone plateau, and it's higher up. Okay, so this plateau is at least 100, if not higher than here, than the plain. Okay, I will show you a 3D image of this because it's very hard to see the different landforms on this image unless you drape this image onto a DEM, and that's what we usually do. Before I do that, I'll show you some picture. When I say plain, this is what the Galapa plain looks like when you go there. It's completely flat. You don't see anything. You don't see any structures. You don't see any, you know, it's very homogeneous. And you can see here the pebbles and the rock fragments. It's called desert pavement. And but you see some variations as you move towards a region where the image, the satellite image, shows some high reflective features, and the high reflective features come from the sand dunes. So sometimes the topography is a little bit or varies a little bit, and where you have some slight depressions, you got some sand accumulation. So here we have the gravel, right? You can see some of them are round, an indication of fluvial activity. And then on top of it, in the depressions, you see the sand accumulation. No? So this region here, let me show here. If you look at this plain, you see variations in color. See that there's a very bright, you know, sort of elongated, you know, linear feature. So the very bright areas usually are either sand or silt, and the darker areas are also surface sediments, but their gravel content is higher. Okay, so there are differences, and we wanted to map those differences, which are not necessarily shown here, using remote sensing. Okay. So let's take a closer look. As I said, this linear bright area here is highly reflective, the same as here. So something is reflecting a lot more light than the surrounding areas, no? And you can see slightly visible these drainage lines. So this is the plateau. This is a cliff, no? This is a cliff area. You see the erosion pattern here, right? And then sort of, it looks like a waterfall. It's not a waterfall, it's maybe a sand fall. It's basically sand that is being blown over this plateau area. And then here, the wind velocity drops because of the cliff, and sand can be deposited, right? And the same here. And here you see the Nile, and also in green, the agriculture activity. But as you see, it stops here. It doesn't continue here because this is higher up, and they cannot divert the river water into the plain because the topography doesn't allow that to happen. And then there is here a wadi system and another one here, and they look like they're connected, but the Nile is basically, nowadays intersecting this older channel, and I will talk about this in a moment. This channel is very important. This channel is a segment of a big river system that existed 10, 15 million years ago. It's no longer, doesn't exist anymore as a river, but the deposits are there. And we are actually interested in understanding the old river system that existed before the Nile actually existed. Before the Nile, there were other river systems. And these other older river systems, they may have recharged the aquifer in this desert plain area. But in order to know that, we need to understand the history of the fluvial history of this landscape. So let's first look at as I said, at the same image, but in 3D. So in remote sensing, it's a very important tool to use a false color image. It's the same image that I was showing you before. However, it was draped over a DEM, a digital elevation model, because it gives us now a three-dimensional, view of the terrain. Very important. Remember when I said to you, the Nile, right, flows, at a certain elevation, and these agriculture areas, they are more or less at the same elevation with the Nile. So the farmers, they can, divert some of the Nile water, and they build irrigation canals, and they can irrigate this part, right? But they cannot do it with the desert plain area here, because there's a escarpment. I don't know if you can see that. There is a small escarpment here, and the elevation between the plain and the Nile is more than 80 meters. It's like 100 and something. And here, this is flat, but there are some variations, topographic variations. And where you have a depression, you've got more sand accumulation here, Aeolian sand. Aeolian sand means wind-blown sand, right? So there are different types of depositions here, or deposition mechanism. One is the wind. The wind brings this, the sand from another source, and then deposits it whenever it encounters a drop in velocity. The wind is no longer blowing at the same strength, and so whatever it's carrying precipitates, no? And that has to do with the topography. And also here you got another escarpment, huge difference. If this is like 100 meters, this is probably 300 meters. And you got wind also blowing over this limestone terrain. And you can see some light colored areas. That's maybe some sand trapped, somewhere here in this karstic surface. And then you can see what I was telling you before, looks like a waterfall, but it's more like a sand fall, right? And here, interesting here to see that the outcrop of the rocky area, and that's more or less covered by fluvial deposits and sand deposits. So we wanted to understand better the nature of this plain. We call it Galapa Plain, no? So here on the left, we have the calcareous limestone plateau. Here very clearly the Nile. And then we got the agriculture activities here. And this is this ancient river system that existed before the Nile. The Nile is now cutting through it, but before the Nile existed, there was a connection here. So we wanted to understand better the fluvial history of this terrain, but we have a problem with the optical images. They don't let us see what's under the windblown sand surface. No? So this is why we used radar. This is a radar image of the same area. And the radar reveals a lot more than the optical because it can penetrate a little bit dry, sandy surfaces. And you see in dark, sort of dark colors, this feature here, no? And it looks more or less like a delta system. And it was actually in previous geological time, it was a delta of a river system here. And if you look closer, you see here the connection now interrupted by the Nile, right? So in the past, there was a river system flowing into this area, and this was the delta system. And actually the coastline was not too far from this delta system. So, the coastline of Egypt also has migrated from the south to the north. And when we look at the drainage system, we can actually get a clearer picture of the present day drainage by looking at the topography and drawing the present day drainage, right? So this was done by in a GIS system. We used a DM, a high, this time a very high resolution DM. You can see here clearly that the DM is mapping all these different wadi systems, and this is clearly the plateau edge. And when we look at the drainage, here's Aswan, and this is where I was telling you there exists an ancient river system that was connected. No, you can see that nowadays there is a water divide right here along this line here, and all the drainage on this side A is now flowing into the Nile up here. And all the drainage system in this part, in this segment B, is flowing into this the Nile, but at this point. So you have now a plain, a desert plain, which looks very flat, but with two basins, A and B, sub-basins, A and B, with opposite flowing direction. One is flowing north and the other one is flowing south, and they both have their outlets in, you know, in River Nile, but opposite direction. This has, of course, to do with the tectonic, you know, forces and which control the terrain. So these lines were mapped by us by looking at the drainage systems and how they are following certain structures. No? And there's some uplift and downdrop happening here, and this has to do with the Red Sea. The Red Sea is a tectonically very active area, and it's causing many, you know, movements along normal faults, right? But although the water right now, well, if there is any rainfall in the plateau area, that is flowing basically from north to south, is following an ancient river channel that in the past was flowing in the opposite direction. Right? It was actually flowing into this direction. And here is a sketch of this ancient river system. So this is a map of river systems in the middle Miocene time, so between 10 and 15 million years ago. I mentioned that the coastline has also changed its position, right? So actually, even in older times, the coastline was not even that far north. It was further south. And what you can see here is, first of all, some escarpments, no, shown here. So this is basically uplifting, right? And then an important river system which has its headwater area here, and it's flowing from east to west, and it's called the Late Kena River System, right? And the Nile River didn't exist back then. It actually existed only a very small section here, right? But it was not connected to the Nile system further south, right? So we think that these river systems may have recharged large parts of the desert area. Some of the ancient, the ground systems are have been mapped, as the case here. So again, to put this into context, Aswan is here, where my cursor is pointing, and this is the Nile, right? And this is the Lake Nasser, right? And the plain, the Galapa plain, we're interested in mapping, in understanding, is right here. So you can see that the geological maps, they actually are showing very detailed information east of the Nile, where the rocks crop out, and you have you can actually see the rocks, and you can see measure the fractures and so on. So this area is, geologically speaking, well mapped. Whereas as you move towards the desert, it's covered by sand, so not much, you don't see many geological features. Let me see how much time I have. All right. And that means we need to use some techniques that allows us to detect what is under the surface. So we need to use some geophysical survey method. And this was the case with the aeromagnetic survey that was done from an aircraft, from an airplane, measuring basically the depth to the basement rock. So here we have, so Aswan is somewhere here. This is the, by the way, this is the ancient river segment that is now cross-cut by the river Nile, no? And this is the part that I showed you before, the graben. This here is right now here, right? And the aeromagnetic survey shows that this graben system actually continues very clearly, very clearly. It cannot be mapped from the surface. You need to have some way of measuring what's under the surface. And the colors, they indicate the depth. And you see, it's a huge depth, 500 meters. This is, the basement is 500 meters under the surface. There's a lot of space here, storage space for water. No? And then, of course, you can start then, drawing these cross sections to understand, how deep these alluvial gravel sands and coarse to medium sand go, right? So you can see that the depth is incredible. That means a lot of storage space if there's still water. And another technique we used is not only geophysics, airborne geophysics, but also the DEM, the digital elevation model. So this is a shaded relief map. Again, we're looking at Aswan. Here's Lake Nasser, here's the Nile. This is the graben system that I was showing you before. And even the topography is showing you that this is depressed. And here we have the Galapa plain, right? Surrounded by the escarpment, right? And this is the ancient river system, right here. And when we look at this with a trained eye, we can start mapping lineaments, fractures. I don't know if you see any lineaments. I will draw them and show you. There's one here. There's actually a couple of them striking in a certain direction. I hope you can see that. So this is very important to learn how to detect these lineaments from these maps. No? And there's another set. And so we were looking for very specific lineament directions where we thought that they might serve as underground water conduits, maybe tapping some of the water accumulated here in the Aswan Nasser, Lake Nasser, and maybe the Lake Nasser is leaking some water that eventually flows into the Galapa Plain. That would be present day recharge. No? So we know that ancient rivers, they recharge this, this aquifer, but it's past recharge. And we are also looking for present day water supply sources. And this is of course one source. This is higher up. So if there are some fracture systems that may indirectly, serve as water conduits and feed this aquifer, that's important to know. So we'll take a closer look at Lake Nasser. Lake Nasser, as I mentioned, receives its water from other countries, especially Ethiopia, right? And there's a seasonality to the amount of water it receives. So here we see the situation in January on the left, and then actually both are January, right? Yeah. But you can see that the water supply has changed dramatically. No? So there's a seasonality. So certain seasons they receive more water and other seasons less water. But there's also another factor playing into the water supply, which is the climate. So if Ethiopia is not getting, the Ethiopian highlands are not getting enough rain, right? That will ultimately have an effect on the water supply to those countries in the lowlands. And this is shown here. So obviously in 88, January, somehow there was not enough recharge happening to the river Nile. But I'm also showing you this, these two pictures to basically show you how we can use that for mapping structures. When the water level is low, we see many more features, right? When the water level is high, they're covered by water, right? And what type of features do we see? Well, we see these lineaments very clearly on the left, not so clearly on the right, okay? So that's an indication that this lake is cross-cut by fractures. They are clearly visible on this side of the lake, right? Less visible on this side. And those, if they are connected to very important long fault systems, they may leak some of the water, surface water, into the aquifer system in the plain area. Okay, so far I've talked about lineaments and the water supplies of the Western Desert plain area, and so on, right? And how we investigate, how the groundwater of the aquifer is being recharged, either in past geological times and also present time. No? And now let's look at a little bit at some other products that can be derived from satellites. And this is just to give you an idea what satellite remote sensing, what type of information it can actually provide to better understand how water is being used, in this case for cropland, right? So here we have some pictures showing you this important agricultural area, and we see that closer to the Nile, most of the fields are very close to the Nile, but some are also, being developed in the more desert area away from the Nile, no? And you can see that they built some canals, and they bring the water all over from the Nile to these fields. So we are interested in knowing how much water do these crops need. What's the water demand? And in Egypt, the agricultural activity has changed dramatically in the last 50, 60 years, right? Way back, the agricultural activity was more or less, sort of slowly increasing, but not dramatically. That changed in 1980. From 1980 on, Egypt has been, consistently and very aggressively being developed. They have been developing their agricultural activity, as you can see here. All these different crop types, cultivations, they go up. Some of them actually, were reduced, cotton and beans and peas, but others, they went up. And this has to do with the population growth. But for us hydrologists, it's important to know which type of cultivation is going up. And when we see these curves, we get very worried, because you see that citrus and fruit, cultivation is going up, and sugarcane is going up, right? And grains. And sugarcane and fruits and so on, they need a lot of water. So the water demand for crops is rising. And then we look at the terrestrial water storage of the Nile basin in Egypt. And we see a trend downwards. So agriculture activity and irrigation demands, water demands for crops is going up, but the water storage capacity is going down. So not good news. This is from another satellite mission called GRACE, and it uses actually the gravity field of the Earth to measure indirectly, the terrestrial water storage of huge aquifer systems. And there seems to be a drop, especially around 2012, and possibly caused by a dry period. There was, that year was especially dry. And so besides of looking at the statistics in terms of what they're growing in Egypt and what's the trend of what type of cultivations they're predominantly using, we also need to understand the water demand of these different crop types. So how much water do they need? And all this will then tell us it's useful information for calculating the water needs. And here's some maps showing how Landsat time series can be used to classify cropping patterns. I'm not going into the details of these classifications because I'm running out of time, but just to give you an idea that certain crop types, they grow at certain months during the year, but there are also crop types crops that are planted twice a year. So this is indicating you in a agriculture calendar year what type of crop is growing, and you can calculate based on that the water demands, no, and also the evapotranspiration. That's another important characteristic. And we can do more than that. We can also look at one single, day, August 2016, and we look at a Landsat scene and classify here the agriculture fields in terms of the type of agriculture. So here we're classifying the fields using a time series along 1 year, every month one Landsat image, and then we convert that into an NDVI image, which allows us to follow the phenological cycle of the crops. So we don't know the type of crops, but we know the phenological cycle. So when the crops are green and when they're harvested. And here we're looking at one single scene, one day, and looking at the crop type, not the phenological cycle, the crop type. And both together indicates, lets us understand the phenological cycle of, especially in this area here. So these are maize and sugarcane. And if you compare that with this map, which shows generally, yellow colors, so it's mostly growing in the summer-winter period. So, and that can then tell us something about how much water is required for this type of crop. Okay, I think I only have 2 minutes. So the next slides are about another type of analysis we did in terms of better understanding actually what's under the surface of this Galapa plain. Again, I indicated the importance of this ancient channel, which was once an important river system feeding this area, feeding the aquifer system in this area. And now I want to show you some slides which will hopefully explain why field studies or surveys are so important to understand, to better understand the images. So far we have been looking at satellite images. Now we're going to look at the field sites. And usually these field campaigns are carried out after you analyze the satellite images, because you need to select the sites where you're going to carry out detailed surveys, right? So this comes after you've analyzed your optical images, your radar images, everything, the drainage pattern, well, everything I showed you before. Once you have analyzed all this material, you're ready to select sites where you go and carry out some geophysical surveys, right? And we're going to carry out ground penetrating radar measurements. Just to show you again the difference between optical and radar. Optical shows you anything that is on the surface. Radar can penetrate a little bit the dry sand, right? And it reveals, for example, this drainage channel here very clearly. You can see it also here, but it also reveals some structures here that are not visible here. This is man-made. These lines are actually electrical wires, right? Electricity, they transport electricity from generated in Lake Nasser to the cities. Okay, so let's take a closer look at the Galapa plain. And remember, this is a Google Earth, so optical. And the Galapa plain has certain areas that are very bright and then surrounded by darker areas. And these are the wind-blown sands. And then we have this ancient river system, right, intersecting this, or the wind-blown sands are intersecting this. And we want to take a closer look at this. And so we use the radar and a technique called interferometric analysis, where we use two radar images obtained different times, and they can be used to detect movements, very slight movements, even at the grain size, almost. And here we see in this map here on the left that using the interferometric analysis, we see which areas, in the plain and also here where you have the wadi, are covered by sediments that are moving, that are basically changing their location, right? And you can see definitely here along the wadi, but also along this linear dune system. The optical, this is an optical image, also in change detection to dates. They don't show you this information. They basically are not able to show clearly movements, change in position. And when you go to the field, this is what you see. It's a surface covered by gravels. But the gravels, they have different shapes. Some of them are round. That's a clear indication of, that they were deposited by rivers, by flowing water. But some of them are, fragments, rock fragments. And then when you go to the area that looks very light, very bright, you see that the gravels disappear and you have sand, right? And we wanted to know whether under this linear dune feature, if there are some structures and what they are. So we ran a GPR survey. A GPR survey is basically, it's a radar system that actually generates its radar beam and sends it down to the ground. And that gives us a way of seeing what's under the ground. So this is the surface. And here we see the horizontal sand sheets. We're standing on this horizontal sand sheet, but the ancient topography, the fluvial topography, was not flat, as you can see here. This is the ancient fluvial topography before the sand got deposited. And there are some important fractures. And here you see the depth. So this goes down 6 meters, right? So you got maybe between 1 and 2 meters of sand right now on top of the ancient fluvial topography. And you do that, in many sites, and then you interpret the ancient fluvial topography and the structures, and you get a better picture. Some of you may ask, can I use ground penetrating radar in, let's say, in a humid environment? Well, it works very well in dry sands. And that has to do with the penetration capability of radar. And there are certain conditions when the radar beam can penetrate the ground better than in other conditions. They're summarized here. So moisture content is definitely an important criteria. The drier the terrain, the drier the sand, the more penetration, but also other criteria. And we did that in some other parts. Here, a high resolution image of another area that is less flat. And here you see the different survey lines we ran. And just to give you an idea of the scale, this is 100 meters. And you basically run these surveys following a certain pattern so that you can basically reconstruct, in 3D how the ancient surface, runs, and also the fault system. And once you collect all this information, again, we're looking at the plain. Here's the River Nile. You are capable of, mapping more fractures than the geological map, actually, the official geological map shows. The official geological maps, they show these lines, and there are no faults were mapped here. With our technique, we were able to complete this information, right? More here because we ran our campaigns mostly in this area here, no? And with this, we can generate what we call a fault density map. And usually these fault systems are important in terms of carrying groundwater. We did we went one step further. We used radar not only to map fractures and understand basically the sediment layers under the Aeolian sand, you know, the fluvial surface system better. You can clearly see with this radar image, here's another channel. This channel is not visible from the ground. This is not the Nile. The Nile is here. This is the Nile. This is an ancient river system here, completely. And this is also this ancient river system and a delta system here. No? We also use these maps to map the composition of the surface sediments, whether gravels, sandy, and what type of gravels, right? And the different colors indicate different surface sediments, which were not mapped in the official geological map. This requires fieldwork. This requires to understand this classification that was obtained from radar. We need to go to the field. We need to run these EPR surveys. We need to take measurements. We need to understand the, you know, how these pebbles and so are deposited, and measure something called paleo current. So the way these pebbles and cobbles are aligned tells us the direction of fluvial, or of basically of water flow. And with this information, we can then map how these different classes, whether gravels, different types of gravels, gravel and sand, how they were deposited, the direction that the water basically, you know, was flowing. And you can see opposite directions. Remember this important line here? This line here, and I'm going to finish with this soon. Let me see if I can do this. Okay, this line here. So basically on the left, I'm sorry, on the right, it's the river system was depositing the sediments from south to north, and on the left, it was depositing the sediments from north to south, the opposite direction. If this actually explains this map here. So the official geological map showed a line. Couldn't explain why you have these two different sediment types, no? And here we kind of get a much better understanding of why you have two different surface sediment depositions there. You know? Again, this requires field work. You know? And by the way, these different gravel types, no? In blue, red, and yellow, and magenta, and green, they're shown here in pictures. So, for example, the first one, G1, looks like this. This is the blue one, the blue. And the red one is G2, looks like that in the field. And then the yellow looks like that. And the magenta looks like this. Magenta is has a lot of limestone fragments. So it's very close. It's coming from the plateau, no? And then in the sand, looks like that. So these pictures, they are key to, the labels. They indicate which picture goes with which legend type or class type. And well, with this, I finish my talk. I'm sorry that I have been taking up all the time. Here's just a few photos showing the some private farmers are drilling for water in the plain and trying to use the water for irrigation, but very rudimentary system, so not highly mechanized, and they are having some issues. And here are the farmers, and we're talking to them, and you can see in the background the desert, and they're trying to irrigate these crops. But not very sophisticated method. But the government is probably going to implement. They are going to implement agriculture expansion here by drilling deep wells and tapping water from the aquifer. So in general terms, or to give you summarize you what I was talking about today. Fluvial Aeolian feature mapping. It's very important for us to understand the ancient fluvial surface, and the problem is it's nowadays mostly concealed by Aeolian deposits, so we cannot see it really very well on optical images what's under the Aeolian surface deposits, but we need to understand what's going on in terms of fractures and sediment, stratigraphy and all, and the depth of the sediment layer and the storage capacity, and all that lets us understand the groundwater, potential groundwater recharge areas in ancient time as well as present time. And radar is extremely important for mapping in desert sandy areas. It gives us a way to understand the fluvial and Aeolian morphodynamics along paleochannels. And yeah, so this region underwent cyclical changes in terms of weather. Wetter and drier climates, they took their turns. Radar mapping is extremely important in these type of environments for detecting faults that are otherwise not visible. And this allows us to detect promising fault zones where we can then, carry out more detailed surveys. We can pinpoint areas that we want to analyze more carefully, and all this hopefully will complete our understanding of the hydrology of the area. And in general, remote sensing provides very useful information about changing water storage, changing land use in agriculture, and ecosystem response to climate change. But definitely more research is needed to examine the impact of climate change on the ecosystem, and also the impact of land use, how we are developing these desert areas for agriculture, and how can we minimize basically the water usage, or carry out drainage, carry out irrigation in a very efficient manner. All right, so this was a long talk. Sorry for that. Not much time for questions, but with this, I will stop talking and hopefully, hear some questions.
Okay, thank you, Professor Magaly, for a very, very interesting presentation about fluvial and Aeolian mapping by using remote sensing technique. Professor Magaly, maybe for your information, that the half of the participants is students who will do geological mapping by using remote sensing technique, and half of them is students that still take geomorphology class this semester. So I think this topic is very, very useful to all of us. Yeah. Before we open the question and answer session, I want to remind all the participants, in case you missed the previous material from Professor Magaly about remote sensing, you can visit our YouTube channel, Geologi Undip, to rewatch those webinars. And now's the time for question and answer. If you want to ask a question, just write your question in the chat box by writing your name, underscore your institution, and underscore your question. Okay, maybe there's already a question. The first is from Miss Devina from Geology Undip. From what you explained earlier, I caught that to get conclusion about the potential for groundwater, not only using remote sensing, what data must we extract from the image before we combine it with the supporting data to determine the potential for groundwater in an area? Yep.
Yes. So so the groundwater system, in order to understand how water is supplied to the aquifer and where does the water discharge or how is it tapped, right? We have to look at all the components, right? From recharge to transmission to discharge. Okay, there's a whole cycle. So how much recharge happens, no? Probably in the highlands, not necessarily in the lowlands, right? And how this water from the highlands, flows into the lowlands, basins, and where does it accumulate? So there are many sections that we need to map, right? And remote sensing can provide a lot of information, but not all the information. We also need to use some other maps. Digital elevation models are incredibly important. We want to combine a GIS analysis of the terrain, right? The terrain gives us the drainage channels. It gives us the slope. It can give us a lot of information also about the elevation, where recharge may occur. We need to know the precipitation. You can actually measure precipitation nowadays also from space, right? And how that precipitation in the highlands will affect the flow in the lowlands, right? We need modeling. Modeling is, we haven't talked about that. There are hydrological models and they can be run in the GIS system. So the radar is really, not only radar, also optical. What I call here radar mapping allows us to map the fracture systems where it's hard to map by going to the field. Now, the potential groundwater is not 100% sure what your question is. So you're talking only about what we can extract from images and how we can combine that, right? So combine it with supporting data. Okay, so there are techniques. I think you referred to the multi-criteria analysis. Have you heard about that? Multi-criteria analysis in GIS, where you basically have a set of maps and you try to understand which one has the highest impact on groundwater accumulation. So you got the precipitation, you got the drainage pattern, the lineament network or fraction network. You got maybe on a map showing you vegetation. Where does vegetation grow predominantly? And you got hopefully information about permeability, if you have one. And you combine all these criteria, and then you evaluate how their importance in groundwater storage or groundwater occurrence to happen. I think this is what you were referring. I'm not sure.
Okay, thank you. And the next question comes from Miss Jenny. In Indonesia, there is a significant land conversion as paddy rice land to the water resources management. Is the main problem will be the water needs for the crops or the loss of recharge area?
So yeah, paddy rice land. Okay, that's, I know that's especially along the coast in the coastal zone. No? To the water resource management is the main problem. The main problem will be the water needs for the crops or loss of recharge. Yeah, well, paddy. First of all, where you can areas where you can grow rice. Usually, the climate is such that you have enough water from precipitation, right? And so I think that in Indonesia, the problem is not so much the lack of rain. It's the fact that along the coast where you have rice plantation, the land is sinking. You have problems with salinization, seawater intrusion. So it's a different problem, no? So yeah, so basically that's what I've seen in Indonesia, in Java, that paddy rice fields have been converted into fish ponds. But this is not because of a lack of water, precipitation. It's because the terrain is sinking and seawater is intruding. You know? So yeah, so it's not so much loss of recharge area, I believe, unless I'm mistaken. Of course, there are climate variability. So some years it rains more and other years it rains less. And then the other important factor in Indonesia is deforestation is happening a lot in the hills, uplands, and that's causing erosion and maybe may have an impact on these rice fields. And what was the other one? For the assessment of groundwater potential using weighted parameters, how to assign value of geological parameter. Yeah, this is the multi-criteria system. So the parameters or the weights, they need somehow to be selected in such a way that the output, whatever you get, you know, makes sense. And how do you know if it makes sense? You need to have some independent source to information source to assess the output maps. No, so for example, geological structures. If your weighted parameter analysis pinpointed that certain structures are potential groundwater carrying structures, well, a way to assess that is by having a well, you know, and knowing how much water, you know, how, can be extracted from that fracture system. So some assessment needs to be done based on field information, ground information. Yeah, it's not easy to. Yeah, to select the weights.
Yep. Okay. Maybe there's still a question you can ask by writing on the chat box. We still have a little time. Maybe from students want to ask about geomorphology, maybe, how to use remote sensing for doing geological mapping? Okay. Yep.
How to what? Say it again.
No. Okay, from Pak Najib.
Oh, Najib, okay. So in summary, you mentioned geophysical methods for supporting geological structural identification. Yeah, what type of geophysical methods? Well, for structural mapping, ground penetrating radar is of course very useful. But there are also, in hydrology, you have many other ways, electric resistivity, for example, and then for mapping, for example, the depth to the basement, if there's an important sedimentary layer on top of the basement, is the magnetic method. If it's a large area, such as Egypt, then aeromagnetic surveys, seismic surveys. They also give you an overview of what's going on under the surface. Yeah, I mean, all the different geophysical methods. And then if you have access to a well, then you can actually use borehole survey methods.
Okay. Is there still any question? Okay. Because there's already no question, unfortunately, we have to end this discussion. But because this is the last time for Professor Magaly to be with us in this webinar series, maybe Pak Najib want to give some words for Professor Magaly? Pak Najib?
Okay, Pak Tri. Wait, I will turn on my camera.
Okay.
This. Okay. Yeah. Now you can see me, Prof. Magaly.
Yes, now I can see you. It's a nice background picture. But actually, both of you, Tree, I know the area of your background. I've been to that area.
Okay. Yes. This is.
That's the Grand Canyon of.
Patri.
Yes, Semarang region. Yeah. Grand Canyon.
Yes, right.
All right.
Yes, Prof. Magaly, on behalf of staff and a student of Geological Engineering Department, I would like to say thank you very much for your time. I believe 5 times is not easy for you to arrange about your schedule. Maybe more, around a half of a semester. A lecture to us is really mean to us about that. And
thank you.
Thank you very much for all. And also, we hope that what all you give to us is enhance our knowledge, and then hopefully next year we can meet offline in Undip.
I hope so.
Yes, we can collaborate for research with lecture in Undip. And hopefully this is online. So next year, you can give a lecture offline to my student.
Yes, I hope so too.
Thank you very much, Prof. Magaly. Thank you.
Thank you. Thank you for the invitation.
Yeah.
That's all. Thank you.
Yeah, thank you, Pak Najib. Yeah, thank you, Pak Najib. Okay, so we've completed the webinar session today. But before we close this webinar, let's take picture together for photo session with Professor Magaly. So please, the participants, please turn on your video so we can take the picture together. Okay, maybe students also please turn on your video, and maybe Mas Reddy or Mbak Jenny can help me to take the picture. Mas Hoki maybe?
Oke Pak Tri, saya sebentar.
Okay, okay, yeah. Please calm down so we can be ready to our own style.
Sebentar. Oke. Sudah Pak Tri.
Okay. Yeah, thank you, Mas Reddy, and thank you so much for Professor Magaly for joining us today, and thank you for the knowledge that you have given to us for the last session of the webinar. Maybe you have given us 4 times, maybe, yeah. It's very, very useful to us. It's very, very precious to us, and we hope to see you again next time. And we all hope that this COVID-19 pandemic is ended as soon as possible, so you can visit us here in Indonesia, so we can meet each other directly.
Exactly. Not only me. I mean, my students are also waiting for
Okay. Yes.
being able to go to Indonesia. I mean.
Okay.
Yes. Yes. Yes.
Yeah, once again, thank you, Professor Magaly, for your time here, and thanks to all the participants for joining us for this NINDA webinar series. Good morning, Professor Magaly. Bye-bye.
Yeah, bye-bye, and thank you so much.
Bye. Thank you.
Thank you so much. Bye-bye.
Bye-bye. Selamat malam ya kepada semua partisipan. Terima kasih Pak Najib, terima kasih Mas Auki, Mas Denny, Mas Reddy, dan semua yang sudah bergabung. Terima kasih juga kepada semuanya ya yang sudah hadir pada malam hari ini. Mudah-mudahan materi yang disampaikan oleh Profesor Magaly bisa bermanfaat bagi kita semua, terutama kepada mahasiswa yang dalam waktu dekat akan melaksanakan pemetaan geologi dengan metode remote sensing ya. Sekali lagi, jika kalian tertinggal dalam materi yang disampaikan Profesor Magaly, mungkin barangkali tentang basic-basic remote sensing bisa mengunjungi kanal YouTube Geologi Undip, cari di sana ya materi webinar dari Profesor Magaly. Ada beberapa tentang basic remote sensing dan remote sensing dalam tektonik dan vulkanik landscape. Ya mungkin bisa jadi berguna buat kita semua, mungkin buat mahasiswa yang masih baru, yang baru mengambil mata kuliah geomorfologi, barangkali ini masih asing buat kalian, tetapi ini jadi salah satu pembelajaran buat kalian tentang remote sensing, tentang geomorfologi ya, karena pada basicnya nanti selama kuliah di geologi, kalian akan sangat sukar menjumpai referensi-referensi berbahasa Indonesia, jadi memang harus dibiasakan dari sekarang untuk membaca referensi-referensi berbahasa Inggris atau mengikuti seminar-seminar internasional seperti ini. Mudah-mudahan mungkin kalau kalian saat ini masih kesulitan untuk menangkap apa materi yang disampaikan oleh narasumber, kedepannya kalian akan lebih mudah dan bisa mengikuti acara-acara seperti ini untuk memperkaya pengetahuan kita bersama. Baik, boleh ditutup ya berarti untuk malam ini, sesi malam ini. Terima kasih atas kehadirannya. Selamat malam, selamat beristirahat. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi
wabarakatuh.
Terima kasih Pak Tri dan yang lain.
Oke.
Sampai
ya,
sekarang.
sama-sama Pak Najib.
Oke.